There it is. That's what I was looking for. Hi, everybody. I'm Chase. How are you? Good. Excellent. This is my first time speaking internationally. I'm really excited to be here. I've loved your city so far. It's been awesome being in Norway. We're going to talk about neural networks, and where do we start? We'll start with me. Hi, I'm Chase Aucoin. That's Chase Aucoin. That's Chase, like the bank, but with less money, so it's easy to remember. Last name, that's Aucoin. It's got a weird pronunciation. It's pronounced Aucoin. That's like oak tree, bottle of wine, but it's spelled like gold, coin, so it's easy to remember. Chase Aucoin. I'm a technical evangelist for App Dynamics. We're an application performance monitoring company. We help organizations all over the world make their software better by making sure that they know how it's performing all the time. So why am I talking about neural networks? We have added a lot of investments in our portfolio whenever it comes to machine learning, neural networks, et cetera, that have really helped empower our customers to be better. And so my goal is, as a technical evangelist focusing with developers, is to help make you guys as good as possible. And so to that end, we're going to talk about neural networks and hopefully inspire you to build products and do things for your customers, clients, et cetera, that change and impact them as positively as we have been able to help ours. So neural networks, that's neural networks. So people are super excited about them. People are just incredibly pumped about neural networks. Every time you get on Twitter, every time you get on LinkedIn, well, I don't know what your guys' social media thing is, but any of those types of things, you're going to see articles, ads, et cetera, for deep network this, new thing that, future is here right now. And that's exciting because we have companies like Google DeepMind, IBM Watson, the scary robot dogs from Boston Dynamics that frighten me so much. And we've made a lot of advancements in a lot of different realms, from medicine, robotics, even things like material sciences. So we've developed a whole lot of new materials that have never existed before, thanks in part to what we've been able to do with technologies like neural networks and machine learning. But first, before I go any further, I want to set a couple of expectations. The biggest expectation is that this is a 100-level talk, right? If you're expecting to get way deep down into the deep downs, that was Seth Juarez yesterday. And I'm not going to talk about any specific frameworks in depth. I am going to talk about neural networks, how they work, and kind of what they do. And my hope with this talk is that if you leave, you go, you know what? I actually understand how they're able to do that. I understand how they're able to do what they do. If you leave here with that, I've done my job well, and I'd like you to give me a green card. So, what is a neural network? Couple of things. Well, there's a lot of misconceptions about what they are and what they aren't. I think the first thing that we talk about is, one, it's just a math formula. And we're not going to talk heavily about the math today, thankfully, right? But that is all it is. I know a lot of people, whenever they first get introduced to it, they think it's a library, they think it's a framework, they think it's some type of programming paradigm. It's not. It's just math. At the end of the day, it's just addition, subtraction, multiplication, et cetera. It's based loosely, very loosely, on the way that the brain works. So whenever we were making discoveries about how the brain does what it does, mathematicians were taking a look at that and said, hey, you know what? I think I could model that kind of behavior as a math formula, which the other surprising thing about neural networks is they're a lot older than many of us think. So most of us, whenever we think about neural networks, we think about this as a new thing. We think about this as a new technology. But really, it's been around since about 1974, 1975, whenever we first came up with neural networks. So why do we feel like they're modern? Why are they so popular right now? I think the biggest reason, or at least the biggest contributor to this, more so than anything, is available compute. To put it into perspective, if you think about 1998 to 2002, and what we had available at that time, top-end PCs for consumer usage, you're talking about just under a gigahertz to max 1.2 gigahertz for a processor. We didn't do a lot of multi-threading. We didn't do a lot of multi-processors. On high-end server machines, we maybe had 2 sockets. On really high-end, maybe 4, but those were very rare at that time. And so now we have GPUs where each core on that GPU is about the equivalent speed of a 1998 processor, except we have 2,000 to 4,000 of them per card. So as an example, my computer I built at home for about $5,000 that has 128 gigs of RAM, a terabyte of solid storage, and 16 cores, alongside with 2 video cards that each have 3,600 cores, so giving me nearly 7,000, well, over 7,000 cores. The equivalent compute, the equivalent compute power in 1998, 2002 would have cost between $80 million to $150 million. So I feel like for 5,000, I got a good deal. So, you know, but having the ability to do that makes a huge impact on what we can do. Secondly, we have frameworks available that help abstract away the math and the difficulties of having to do things like program massively paralleled math equations across many cores, right? So traditionally, whenever we think about trying to do that, before we would have had to spend a lot of our own time building out just the infrastructure on how do we pipe data around all of these processes in order to actually make the algorithm work. But with frameworks like TensorFlow, et cetera, that has kind of been abstracted up and we don't have to worry about that so much. And then lastly, automation. Business tends to drive a lot of leadership in this space, and automation is a big part of business right now. Businesses want to try and get the most out of the resources that they have available. And in many ways, we have shortages on different aspects of what we need as businesses. And so our goals and oftentimes are to automate as much of that as possible so that we can secure further growth and development. So between those three, having so much compute availability, the ease and access to frameworks and libraries, and the ability to leverage all of that compute alongside with the business motivators to do that, it's kind of created a perfect storm. But with all of that out of the way, let's actually talk about the parts of a neural network. I'm going to focus on 5 main parts of a neural network. Inputs, outputs, weights, biases, and the hidden layer. There are other parts, but again, this is a 100-level talk. I'm just not going to cover everything, and that's okay. First, we're just going to talk about these 2. We'll get to the others, but these 2 are the most important for right now, inputs and outputs. We should pretty much all be familiar with that as developers as far as what inputs and outputs are. But in the context of machine learning, and especially with neural networks, we want to think about it a little bit differently. Inputs are what we already know right now, some sort of data. We've got some type of data that we know right now, and then what we want out is what we want to know about that data, or how we want to map that data into something useful for us. Neural networks are incredibly powerful and incredibly good at mapping disparate data and creating pathways from point A to point B. They're really good at making complex mappings of data. And so whenever we think about our inputs, we can think of it really as any arbitrary data. And we see images used a lot, but I like images as a use case simply because it's an incredibly arbitrary piece of data to everything but us, right? We have a bunch of numbers ranked from 0 to 255 in a row that somehow we interpret as a dog, right? That's kind of incredible in a lot of ways, but to put that expectation on a machine without any kind of foresight on its part seems difficult, right? And so whenever we look at an image, we see things that make it dog-like, the way that the eyes are, the way that the mouth is, the way that the hair is, et cetera. And so our goal is to extract those types of features and get something meaningful out of it. So our outputs will be some type of classification, whether it's a dog, a cat, a baby, something else, right? So it's what we want to know about that arbitrary data. That relationships between what we know and what we want to know is the neural network. That is what we are building. And so in this case, those pixels represent a dog. In this case, those pixels represent a cat. Neural networks map inputs to outputs. So we do this by training from data sets. We'll take a whole bunch of known inputs and a whole bunch of known ways that we would like to map those inputs. And then we run it through, And then our goal is to create a network in the middle that maps those inputs to those outputs in a generalized way so that we can then reuse it. So how do they do this? How do they actually do all of this complex mapping? Well, predominantly through the weights. The weights are the part that help us actually map the data from our inputs to our outputs. So why do we do this? Why do we need weights? What do we mean by weights? This tends to confuse a lot of people whenever they first start talking about weights because they see them, like, I don't understand what these are, how these fit in. Weights help us control the flow of input data. And we can see this if we step away from like a whole neural network and we just focus in on 2 points of data, we can do things like let data flow through exactly as it is. Or we can do things like throttle that flow of data. Or we can do things like stop it entirely or amplify data, right? So we can change the values of our input data just by adjusting those weights. Well, weights help us influence the signal of our input into something that is more meaningful. And to put this into perspective, audio engineering is a good way of looking at this. So if you think about an equalizer, you can have a whole bunch of different bands of equalizer. The most common is probably a 3-band equalizer. This is what most of us have in our car. High, mids, lows, that's it. And we can somewhat affect the sound shape by adjusting those 3 levels. Now with something like a 30-band EQ, we can really drastically change the way that the way that the sound comes out by boosting and limiting different parts of that input. So we can visualize this a little bit using the color wheel. Let's say we have red and blue, and we want to combine those into something meaningful. Well, if we do them in equal parts, we're going to get a magenta or a purple. Or if we limit the weights on the blue, we'll get something that's more of a rose color. Conversely, if we limit the weights on the red, we're going to get something that's more like violet. Or we could remove the red entirely, or conversely, remove the blue entirely, right? So if we decided to look at this instead of just the names and as a set of input values, it becomes more clear because then we can do things like limit the amount of red that we are inputting, and with weight set at a 1, it's going to flow out exactly as it came in, right? But we can do things like boost that signal. So if we wanted a brighter red because our reds are often dull, or perhaps we want to do things like saturate that red. Our weights let us change and blend all of that. And if we start to add some blue back, we get an entire new spectrum of color. We get pinks all of a sudden. And so if we put about half of our total weight of our blue in, we're going to get a hot pink. And then if we limit the amount of blue that's already coming in before that weight, we're going to get something that's more like a neon pink. So with just these 4 values, we can create an incredibly wide spectrum of colors just by blending and shaping that different value. So who sets the weights? Do you set the weights? No. The way that we set weights is by that training that I referenced earlier. So as we are inputting all of what we know and what we want to know, our frameworks let us adjust those weights to change the flow of the inputs to create those meaningful outputs. That mapping, that relationship, is the network part of neural networks. We can envision this like this. So we have inputs and outputs, and then we have connections in between them. This is typically known as a dense network because every input is connected to every output. Sometimes it's hard to visualize this with all of it connected, but if we look at it individually, our first input is connected to all of the outputs, second input is connected to all the outputs, third input is connected to the outputs. So this is what's known as a dense network. Let's say we want to do something meaningful with our network. Let's say we actually want to get some value out of it. Conceptually, this is all starting to make sense, but what if we actually want to do something useful? So let's say we want to find the triad. On the color wheel, the triad is 3 points of colors that are in this format. So we have primary, tertiary, and secondary colors that if we move around the wheel are our primary colors. We're going to just focus on 3 just to make it simple. Our primary colors, red, blue, and yellow. And we have a dense network in between them. And what we want to do is find the triad. So for 2 inputs, we want to find the matching third output. And the weights for that would be pretty easy to conceptualize. Red is not the third part of the, is not one of the inputs that we would want to match the 3. So we're going to go blue and yellow for an output of red, red and yellow for an output of blue, and red and blue for an output of yellow. And so by adding those zeros in there, we have effectively pruned our network. And so instead of looking like this, now it looks more like this. The connections are still there, but they're just not letting any data flow through. So whenever we talk about classification, generally our goal is to find whichever value has the largest amount. And so with those values now inputted, we're going to find that we get a value of 1, 1, and 2. That 2 being our highest value, yellow is the correct answer, and yellow is the correct answer. We did it, good job, woo, yeah. But what if we wanted to adjust it further? What if we wanted something that was less fuzzy? Right now we have a kind of fuzzy answer. We got a 1, a 1, and a 2, that's all right. But what if we need to adjust that further to get something even more meaningful? Well, then we can use a bias. So our bias lets us shift values around in a meaningful way and into different parts of the number line. So if we have a bias of -1, all of a sudden these outputs shift, and now we have something even more meaningful. It either is or is not what we want, right? So instead of it being a fuzzy thing, now it's a very concrete, hardened thing. It either is or is not yellow. So with our current setup, we could only ever solve incredibly simple problems doing this. But what if we have a more complex problem? What if we have much more complex problems? That's where hidden layers come in. So next to weights, hidden layers are probably the most confusing other thing. Like, what are they? What do they actually do? If we think about a simple math problem where we wanted to take the difference between two values, y minus x, and then we wanted to multiply those by 2. It's a fairly simple math equation. In this case, 5 being y, 3 being x, it'd be 5 minus 3, that's 2, times 2, that's 4, right? Pretty simple. But the problem is, and if we wanted to visualize this as a function, it would look like this. We take in our x and y, we take in our difference, and then we take that out. The thing that's notable here, there's no way to do this in under 2 steps. We can put it in one line, but 2 steps are always going to happen. We have to always do at least 2 steps, right? And so no matter how we adjusted the weights, no matter what format we put the weights in this dense network, we could never get the appropriate output. It would just never happen. That's because we need to add more complexity to our network. And so if we add some additional nodes and we affect the weights of those, we can then solve our problem by adjusting the weights for those nodes. And so all of a sudden we have a reusable network where when we put 3 and 5, we get 4, or we put 1 and 9, and we get 16, which are both the correct answers. So now we've created a reusable network by adding some additional complexity to our network. If we want to look at this from an architectural view, typically whenever we see folks looking at neural networks or showing what they've done, they may have some type of architectural diagram that is similar to this. And so this is what our very simple neural network that's doing our math formula would look like. And from a conceptualization standpoint, it's inputs, outputs, inputs, outputs, inputs, outputs. And really it's just those simple relationships in between those two that filter data down, filter data down, filter data down into something meaningful. And if we were to look at the same kind of concept from a code standpoint, we have inputs, outputs, inputs, outputs, right? So we don't really know in advance what those values should be. We don't know in advance what the values for the hidden network should be. We don't know in advance what the value should be for our hidden layers. That's why they're called hidden, is because we don't care. We don't know, we don't have to know, we don't care what's going on in there. All we care about, all we should ever care about, is what's happening with our inputs and our outputs. That's the most meaningful part, because that's the part that you control, that's the part that you have the most ability to affect. And this is why when we talk about data science, and in particular with neural networks, we talk about garbage in, garbage out. If you have garbage inputs, you're not going to be able to create very good relationships and good mappings. Now, that said, even with garbage inputs, with a sufficiently large enough network and a sufficient number of time, you could, but that's ultimately inefficient. So with it formatted like this, where we're having multiple of these layers going down, this is considered a deep network because we've added multiple layers down to filter. There's also a concept of wide networks, where instead of going deep in that way, we can go out the other direction. Neural networks can, in theory, approximate any mathematical function. And that's why sometimes they're called universal function approximators. Now, that may not sound that interesting because you're like, well, if all it can do is just approximate math functions, I don't care, right? If you think about what you do as a developer, whenever you compile code, you're compiling that down to processor instructions that are ultimately just doing very simple math, right? Everything that, no matter how complex your logic is as a business or what you're developing as a developer, all of that ultimately is being drilled down into math formulas that are executing on the fly as very simple math equations. And so from that perspective, if you step way back, you can, in theory, approximate any function. So those are kind of the 5 main parts: inputs, outputs, what we know, what we'd like to know. We want to connect our inputs to our outputs. We want to be able to shift that data around into something more meaningful. And then we want to be able to add complexity to our network to solve more complex problems, to create more deep relationships in our mappings. So how do I do it? How would I go about making a neural network? There are a ton of options out there. We have CNTK, TensorFlow, PyTorch, Theano. PyTorch is getting a lot of press right now. And it kind of depends on what you're doing and how you're doing it. For me and most of the projects that I personally work on, I'm a big fan of Keras. And the reason is it's an abstraction layer that sits on top of other libraries. So in the case of TensorFlow and Theano, Keras sits on top, and it creates abstractions about how we conceptualize neural networks, but it doesn't implement them. And it passes that implementation off to some other vendor. And the reason I like that is that if we get new and improved ways of running those graph libraries of executables, we can leave our code the same, but swap out the back end. It also makes it easier because we can assemble our neural networks more like bricks and building Lego castles instead of having to put on our mathematician hats and feel like we're in a beautiful mind with a big library of got all kinds of equations and stuff. We don't really want to do that. We've got not a lot of time, and so we want to make as much use of it as possible. So what if we wanted to take just our very, very simple network and make that in code? Well, what's great is we can do that in just 10 lines, right? It doesn't have to be a complex thing. It doesn't have to be an unmanageable thing. So we take our Keras, we import that. This is in Python, by the way. We have our inputs and our outputs, and here we've just done 2. In reality, you need much more input data and the matching output data that goes along with it. So that would just be an array of your inputs and your outputs. For a model, we're going to do a sequential model. Sequential in the context of Keras means that this layer is going to happen first, then this layer, then this layer, then this layer, thus providing that kind of filtering of data. So we're going to use our dense layers, and then the units are how many of those circles, how many nodes we would have in that layer. So 2, 1, and 1. Then we have 2 other lines that we'll talk about in a minute. So what this would look like with the code next to the visual, we'd have our inputs, we'd have our dense layer, and then our output. And so it's really pretty easy. And even if you're making incredibly complex networks, you can still do that same kind of thing, because ultimately we're just trying to filter data down. And the other thing I like about using Keras is it really drives you to have to focus on your inputs and outputs, not so much on everything else. So let's talk about this line, right? So we've got these 2 lines, compile and fit. Compile, this is where we are taking our abstraction and we are matching it to our implementation. So we're going to actually turn that into something that's usable by the CPU and the GPU. Our loss and optimizer, we'll talk about in just a second. The other thing we'll talk about is fit. All fit is doing is literally saying, I want to fit my inputs to my outputs. I want to match my inputs to the corresponding outputs. I want to fit the weights so that they create a mapping that makes my inputs go to my outputs. Epochs is how many times do I want to run it to match those up. So let's talk about loss and optimization. We're not going to spend a lot of time on this because, again, this is a 100 level talk, but loss is the measurement of how far a prediction is away from what you wanted. So we have our outputs that we're putting, and then it's got its prediction that it's making, and initially, those are going to be way different. Those are going to be way off. And we want to adjust the weights so that that gets closer and closer. Our optimizer adjusts the weights to reduce loss. So loss is how far am I away from being correct. Your optimizer, its goal is to make the weights adjust in a way that makes you more and more correct over time. As a beginner, if you're just getting into this, by and large, for most situations, you can get away with just using mean squared error, that's that MSE, and an atom optimizer. We won't get into what those are exactly. I think what's more important is that you actually get out there and use the stuff than to like spend a lot of time, what does this mean? I don't know. It doesn't matter that much. And that said, once you get past beginner status, after you've started playing with it for a little bit, then you want to deep dive into that stuff. Absolutely do it. But what I'm saying is don't let it be a limiting factor for you not to just like go ahead and try, right? If you can just get started as soon as we leave this room if you want to, right? Take some inputs, take some outputs, try to match them together. Let's talk about cows, right? I think cows are something that we don't talk about nearly enough in the field of machine learning. I'm from rural Arkansas. I graduated second in my class in high school out of 12 people. So very rural area, farming community. I think cows are important. But what if we wanted to know what kind of cows these are? Clearly, they're all brown cows. That's what kind of cows they are. But no, there are very distinct types of cows. So we would want to use what's called a classifier. We take our inputs of our pixels of our cows. In this case, we're just using black and white to make that simple. If we wanted to use RGB, it'd be 72 by 72 by 3, right, RGB. In this case, since we're just using black and white, it's going to be 72 by 72 values of 0 to 255. So the shape of our inputs is 72 by 72. We would have some type of dense network in the middle, and the units are kind of arbitrary. That's where testing and all of that comes in. And then outputs, we're going to have 3 outputs. Either it's a Guernsey, a Longhorn, or a Highland cow. And we want to represent that in a way that we can actually use numbers. And the easiest way to do that is either is or is not a thing. And so it's either a 0 or a 1. And in our case, it's a 1. So that would be a Longhorn. And yes, that's correct. That is a Longhorn. But what if we wanted to predict milk cells, right? So we've identified what all our cows are. Now we want to start selling some milk. But we need to know what the future is going to look like a little bit. Well, this would be forecasting, and there's some ways that we can do it pretty simply. Let's say we've got the last 30 years of milk cells. What we might do is take that into chunks of 6 months at a time, and we would overlap those 6-month periods. So we would have a whole bunch of inputs of 6 months, and the idea would be to predict the 7th month. So we would take in our 6 months of sales, and then our output would be whatever the 7th month is. In this case, we're going in millions of sales, but we've reduced that down to a smaller figure. And so we have our inputs, we have a dense layer with some amount of hidden nodes, and our outputs are just one value. That's whatever our 7th month is. Easy, right? None of this is hard. It's pretty easy. What if we want to find contaminated milk before it's shipped? This is anomaly detection. I'm not going to put up a diagram on how that works because it's a little bit more fussy. But basically what you would do is you would find a whole bunch of different samples that are what good milk looks like, and then you would pass that through, and you wouldn't really ever give it any samples of bad milk. And you would have some expected outcomes from it, and then if all of a sudden those expected outcomes were like way different, you'd say, okay, this is a flag. There's an anomaly. Something is wrong. Something is not doing what normally goes through here. What if we wanted to estimate the price of a cow at auction? So we've raised them. Now we want to go sell them. We can take all of the features of our cows, represented as numbers, so whether that's weight, age, breed, diet, etc. We can take all of the available input that we have, and then we can put some amount of units in the middle, and then output, we just one unit, and that is our estimated price per pound. And this will be called a regression problem. So ideally what we're trying to do is match features to a single value. Now what's cool is you can go the other way around too. So if you wanted to do price per pound as your inputs for previously sold things and match those to features, you can do that too. It's gonna be a lot fuzzier, but you can do that. So that way you can find things like, oh, if I want a really high valued price, here are the features that I need to look at most. But what if we wanted to automate that auction process? This is where reinforcement learning comes in. Reinforcement learning, I think, is probably the most important, where a lot of the most important advancements in this tech stack are coming. Reinforcement learning is, as a whole, is way beyond this talk, because it does get a little bit complex. But that said, what's cool about it is it's basically you're training networks to play games, right? And this is where we find things like AlphaGo, the Atari playing robots, etc. We take a bunch of states, what's going on right now, and we match those with possible actions that create some future reward that is high, right? And so what's cool about reinforcement learning is instead of traditional types of learning, where we take a whole bunch of known inputs, known outputs, what we're trying to do is create actions which create the highest possible amount of future reward. Why that's cool is you can create really rich, deep logic inside of your network without it ever knowing how to play the game. You don't ever have to show it the rules. You don't ever have to show it anything other than here are actions that you can do. Here are states that you know about. You're either doing better or worse, right? And then it's going to try to continue to do better and better and better. And so, as a kind of very thin example of what this would look like, we'd have states, our current bids, cow information, sentiment analysis, et cetera. We'd send that through, and then we would have an output and action to take. Increase bid, take bid, whatever our available actions are to do. The reason I think this is a game changer is traditionally with machine learning, it's been a supplement to kind of traditional statistics. A good example of this is sales. So let's say we're a sales organization and we know that our best clients, our clients that are most prone to buy, because we've done the analysis, are people that make between $50,000 and $75,000 a year. They're the most prone to buy, right? We've done that analysis ourselves. And then we've got some data that's got holes in it, and we don't know how much these clients make, or potential clients make, but we know how much some of them make, and so we say things like, okay, well, I want to fill in these holes and find out who of these probably make $50,000 to $75,000 a year. That way I can market to them. That's what we have traditionally done with machine learning, right? So we've tried to use it as a way of filling gaps of knowledge and such like that, and kind of augmenting what we do as statisticians. But with this, we can do something incredibly different, which is, hey, here's all of our customers, here's all the data that we have about all of our customers, here's a set of actions that we would like you to be able to take with those customers, and we want to maximize profit, right? So instead of saying something very specific where we're interjecting our own hubris into it, we can ask more vague questions that are hard to map out, right? So it's very difficult to map out what exactly you should do in order to increase profit. We all have our own ideas about what that is within our own organizations, but reinforcement learning allows us to create agents that can do that for us. And so I think that for my personal money, that's where some of the coolest developments are. What we're at AppDynamics are doing currently with machine learning and neural networks, we've made big investments into the space, and we're in the application performance monitoring industry in general. all the companies have gotten good at getting us to a point to where we know what's going on right now. We can show you exactly where in your code things are going wrong right now, what you should fix in order to make things better. We can do that right now. That happens today. But what we're trying to do and what we're like to do and what we're going to unveil later this year and into next year is the ability to say, here are things that are going on in your system that are going to fail. Here's where you are going to have major problems. And here's how much it's going to cost your organization. Because we want to be able to empower you guys for success so you can get well ahead of all of those problems. And so we're doubling down our efforts to make that happen. We've already had good results in our beta and alpha tests with our customers. Again, that's why I think it's valuable for you guys to hear these kinds of stories so that whenever you go back to your organization, you say, look, other companies are investing in these types of technologies. They're already getting rewarded by it. Maybe we should think about investing in these types of technologies. So a couple closing thoughts. I think the space is incredibly good to be in if you are a developer, if you're anybody. I'll say this, it's not limited, right? It doesn't matter what your background is. It does not matter at all what your background is. Anybody can get into this stuff. Anybody can do this stuff. Especially with the frameworks that exist now. You don't have to have a deep mathematical understanding. You don't have to have anything other than a willingness to learn and a willingness to try and fail, right? Because that's probably the biggest part of all of this is creating a hypothesis, trying it out, failing, doing it again, right? And just keep doing that. So please don't be afraid to try and be wrong and just go out and do it, right? Go be dangerous. If you'd like to get in touch with me, you can reach out to me on Twitter at any time, at Chase Aucoin. I would love to answer any questions and stuff that you guys have. I'll take some here, and then, of course, I'll be available the rest of the event. If you'd like to check out AppDynamics, we have a booth down there. We'd love for you to check us out. That's where you clap. All right, who has questions? Anyone? It's hard to tell. No? All right. Cool. Oh, you have one. Excellent. Yes.
Is there anything important to know about preparing my inputs? Perhaps, like if I have stuff that's too disparate, is that a problem? Should I try to narrow things in?
Okay. So the question was, is there anything I should know about managing my inputs? Let's say I have disparate data, things like that. The disparate data is not as big of a concern as is the standardization of that data. So if it is disparate in the size of it, then yes, that does matter. So if you've got some values that are in the tens of thousands and others that are in the hundredths, those ultimately aren't going to be compatible because the network will favor those higher values more. And so we want to do what's called standardization, where we take those and kind of put them on the same playing ground. The most common way to do that is just to scale them. And we scale by taking our highest value, our smallest value, and then match those to some other new sets of values, typically between 0 and 1. And so that way all of our inputs are in that scale of 0 and 1. They all kind of have the same influence on the network. It's a great question. Thank you. Any other questions? Up top. The question was, for a beginner, where would I recommend getting started on reinforcement learning? There is a course on Udemy, I believe, by the University of Georgia that is probably my favorite video course. Really does a good job. Now, it is math heavy. I'm just going to give you a big warning on that. Super math heavy, but great course. Really gets into the nuts and bolts of how reinforcement learning works, why it works, et cetera. But great question. All right. I don't see anybody else. All right, guys. Thank you so much. Have a great rest of your conference.